Okay, in this video I'm going to be talking about parametric equations as they appear in Calculus BC. Also can be vector equations. It's the same thing. And today we're going to look at, slopes, concavity, arc length, things like that for parametric equations. The two-dimensional motion problems, which is really the bulk of how this stuff appears on the exams, is something I'm going to save for the next video. So the first thing I'm going to do is just go back and talk about parametric equations in general and graph one of them. So the first one I've got is going to be, give a sketch of the graph of x equals, t to the third minus 4t. And y is equal to 2 minus t squared. And what I'm going to do is, just like any other graph that we're not sure what it looks like, the best thing if we don't have a graphing calculator is to make a table, plot points, and connect the dots. Now the thing about a parametric curve is it's going to have some orientation to it. It's going to, be a path that has kind of a starting point and then an ending point, depending on the domain. And so maybe I will say that the domain of this thing will be -4 to 4. So t is in the interval -4 to 4. All right. So I'm going to make a table, except instead of 2 columns, I'm going to have 3 columns. I'm going to have a t, an x, and a y. All right. Now I'm hoping this is enough to get the general picture. If it's not, I know what this thing looks like, so maybe we'll come back in with a calculator in a few minutes and look at a different way to graph these things. Okay, so when t is -4, I take -4 to the third, and that's -64. That's not looking good. And then plus 16, yeah, that's really negative. That's off the graph. Okay. And looks like I need to actually, I used a graphing calculator and made a table and did this, because this is a pretty fast-moving graph. The shape is kind of what I was interested in showing y'all, so I just filled in the table for you. I rounded off 5.625 to 5.6, and I think this should give us a pretty good picture of what's going on here. So when t is -2.5, x is -5.6, so you go over here, 3, 4, 5, and some, and y is -4.25, so that's, say maybe there. Oops, there we go. I don't know why I'm having trouble coloring. There we go. And then when t is -2, we have 0, -2, so see, I moved a long way. And then at -1, it's 3, 1. Bless you. At t equals 0, it's 0 and 2. Okay. -3, +1, and so I think now would be a good time for me to, okay, I started here, I went there, and I looped around, I'm there now, and since I started there and t is increasing, we say it has this kind of orientation, and so we just draw some arrows on the graph. Okay, so then when t is 2, I'm back to 0, -2, okay, so I've kind of looped around there. And it's looped back on itself. And then 5.6 and -4.25, well, that would be around here. Again with this. All right, there we go. All right, so. And if we're doing -4 to 4, we knew it came from over there, and it's going to go off pretty quickly. But this is a graph that loops back on itself, and that's a perfectly fine sketch. In fact, that's probably more sketching than you'll be asked to do. Okay, so now that we've made a graph of one of these things, I'm going to show you the different representations that this thing can look like. Okay, so we've written it as parametric equations. So if it's parametric equations, it's an x equals some equation involving t and y equals some equation involving t. It looks something like x of t is t to the third minus 4t, and y of t is 2 minus t squared. Okay, we can also write it as a vector equation, where we just kind of put the information about x and y together. And that's what the vector equation would look like. Right? We've just put the information about x of t and y of t in their proper order. We've put some kind of pointed parentheses around them. You can also use regular parentheses. I prefer to use the angled ones because it distinguishes between a point in the plane and a vector, which, similar, but there are subtle differences. All right, so I think now would be a good time to look at the slopes of these things. Okay, so we want to find the slope of a parametric curve. And so we want to find the rate of change of y with respect to x. But y and x both depend on t. So there are times where you can eliminate the parameter and, take a parametric curve and write it as some function of x on a limited domain. But there are also times where that's not possible. In fact, I believe that the first graph that we wrote down is not going to be something that you can write as an explicit equation for y in terms of x because it's not a function, right? You can see that it definitely did not pass the vertical line test. Okay, so what you do is you take the rate of change of y and just divide it by the rate of change of x. It really is that easy. It's what you would expect. It's y prime, wrong color. Y prime of t over x prime of t. Or you take the derivative of y with respect to t and you divide it by the derivative of x with respect to t. So the first example I've got is number 3 from your multiple choice packet, and it says x is t squared minus 1, y is 2e to the t, find dy dx. Okay, this is a question that I want, if we were encountered with this on the AP exam, I would want 100% of us to get this one right because this is really just a derivative question. So what you do is we know that dy dx is the derivative of y divided by the derivative of x. Okay, so what we need to do is we're going to need to find x prime and y prime. Okay, y prime is 2e to the t, and x prime is equal to 2t minus 0. Okay, so when I go to, divide those, I'm going to get 2e to the t divided by 2t, which is the same as e to the t over t. And which answer choice is that? Okay, that's A in your packet. Okay, next I want to talk about times where a parametric curve could have a vertical or a horizontal tangent. Now, we remember from earlier in the year, mainly when we were doing implicit differentiation, that a vertical tangent happens when dy dx is undefined, specifically because of division by 0. And so knowing that dy dx is y prime divided by x prime, well, that would mean that this will happen when x prime of t is equal to 0. Now, I'm going to also tell you that y prime needs to simultaneously be non-zero, but I have not seen any items in this course at this level that are dealing with what happens when both derivatives are 0. What I will say about it is that when both derivatives are 0, the behavior is kind of unpredictable, so it might not be vertical. We've seen so far in this course many cases where 0 over 0, it's not infinity, it's not 0, it's, it can end up being a lot of things. And then the horizontal tangent, that happens when dy dx is equal to 0. Knowing that dy dx is the derivative of y divided by the derivative of x, that's where we can see, okay, we're going to need the top to be 0, so we need y prime to equal 0, and we need the bottom to be non-zero. That's what we need for a horizontal tangent. The next example I've got for you is number 20 from the multiple choice packet. So for what values of t does the curve have a vertical tangent? Okay, so we're looking for a vertical tangent. And we know that that happens when dy dx is undefined because of division by 0. Okay, so we need x prime equal to 0 while y prime is non-zero. Okay, so what I'm going to do is I'm going to do some work on x and y. I'm going to get x prime, and that's equal to 3t squared minus 2t. and I'll just take y prime because it's easy and I might need it later. That's 4t to the third plus 4t minus 8. Okay, so it's like, oh, that's not factorable. I wonder what I'm going to do with that. Okay, so x prime is what we need to equal 0, so I set this thing equal to 0. And maybe I'll also factor at the same time. And I'll say that x prime is equal to 0 when t is equal to 0, or when 3t minus 2 is equal to 0. Okay. So these are, times that x prime is 0. I need to make sure that y prime is not 0 at those times. Right? Because you can see on the answer choices, they've got, different combinations of different numbers. It's like, only one of them, two of them, three of them. They've got t equals 1, which is interesting. But I believe that would be if you were looking for where y prime equaled 0. That's going to be a place where y prime equals 0 is t. But we're not interested in y prime equals 0. We want x prime equals 0. What I do first is I'm going to just test y prime of 0, just to make sure it's not 0. That's equal to negative 8. That is not 0. Okay, so t equals 0 is a place of vertical tangency. And then y prime of 2/3. This is where I got tripped up yesterday. It's like, oh, I don't really want to take 2/3 to the third power, multiply it by 4, add with common denominators, and then subtract 8. But pretty much you've got negative 8, and then you're going to add 4 times 2/3 to the third, which is 8 over 27. So that's less than 4, right? And then you're going to add 4 times 2/3, which is also less than 4. So in terms of the positive numbers over here, I've got a number less than 4 and a number less than 4. Together, that has to be less than 8, so this has to be negative. I don't know what the actual value is. I don't have a calculator nearby. So I can say it's less than 0, therefore it's not equal to 0, and I'm happy. So knowing that it's 0 and 2/3, that's answer choice C. All right, so the concavity of a parametric curve, we're going to find the second derivative of y with respect to x both times by first taking the derivative of dy dx with respect to t and then dividing by dx dt. Okay, as far as the derivation of this or whatever, I might include that in a separate video, or you can kind of go through and manipulate the symbols on the equation in blue and see that it does work. But for now, I'm just going to show you some examples. So multiple choice number 14. X equals t squared plus 1, y equals t to the third. So I went ahead and just gave you dy dx. That's 3t squared over 2t. And what I'll tell you is, in this class, we don't really need to simplify all that often, unless, you need to recognize the correct multiple choice answer choice, or you want to save yourself some time or effort. And this is a place where you can save yourself a lot of time by just canceling off 1 power of t. Right, because I know that if I left it like that, I would have to use the quotient rule, and that's just something I don't feel like doing. When you go to find the second derivative a bunch of times, say on the homework or something, you'll get plenty of practice using the quotient rule. Leave that for then. If this one's easy, just let it be easy. So this is 3/2 t. Now we know that getting the second derivative, that's what the question was asking for. To get the second derivative, you take the derivative of dy dx, and then you divide by dx dt. And everyone wants to forget to divide by dx dt. Forgetting to divide by dx dt is always going to be an answer choice. Let's see, number 14, I'm kind of flipping back in here. I'm seeing, yep, answer choice E, 3/2. That is not the right answer choice. Right? That is wrong, and probably the most commonly chosen of the distractors. So what we're going to do is we're going to take the derivative of dy dx. Okay, so take the derivative of 3/2 t, and that's just 3/2. And then we divide by dx dt. Well, dx dt was 2t. So that's 3/2 divided by 2t would be 3 over 4t, which is, where is it? Answer choice A. And next we have arc length. Okay, we remember from a couple units back when we did area, volume, perimeter, that if we had some function, y equals f of x, we could find the length of the graph by integrating between two x values the square root of 1 plus dy dx squared. Now, you might remember how I generated that formula. I'm going to do the exact same thing, except I'm going to draw, maybe a parametric curve with some excitement. Kind of like the one we drew earlier. Maybe I'll do, I don't like that. I'm going to do it like this. All right, so maybe, maybe it's even got some orientation to it. And then there's this small piece of arc length that we're going to approximate with, a straight line. And we're going to add up all of those and, with a Riemann sum, and then eventually it's going to turn into an integral as we add smaller and smaller pieces, and the number of pieces goes towards infinity. All right, so what I'm going to do is I'm going to kind of call this length delta p for a small piece of arc length. And we know that the length of delta p is given by the square root of, well, what? Okay, so I kind of pop out this delta p and get an enlarged version over here. Looks about the same. And as we're going to the left, that looks like that's dx dt. And we're going up, and that's dy dt. Okay, yeah, that should not be dx dt or dy dt at this point, right? Eventually it will be, but this is delta x and delta y. And the length of delta p is given by the square root of delta x squared plus delta y squared. Very sloppy. And so I'm going to find this length by adding up all of these delta p's. Okay, so this is the sum of a bunch of square roots of delta x squared plus delta y squared. But this is, it's kind of missing some stuff to be something we can turn into an integral. So what I'm going to do is I'm going to multiply by a clever form of 1. Which would be delta t over delta t, right? Because all these things depend on t, so if I'm going to integrate, I'm going to have to integrate with respect to t. But even still, this delta t in the denominator is not really doing me any good. So I'm going to replace that with a square root of delta t squared. Very similar to how I got the formula for arc length of a regular function. And so what that's going to end up being is I'm going to distribute that square root of delta t squared into the denominator, or make it a denominator. And so that would be delta x squared over delta t squared, and delta y squared over delta t squared. And then I'm still left with that delta t on the outside. And as the largest piece of arc length, gets shorter and shorter, and the number of pieces goes towards infinity, this is going to turn into an integral between two t values of the square root of, okay, delta x squared over delta t squared. Well, that's going to become dx dt squared. And delta y squared over delta t squared, that's going to be dy dt squared. Okay, and so that's our formula for arc length of a parametrically defined curve. So I went ahead and took the time to highlight that for you because that's something we're going to need to commit to memory. Okay, the example from the multiple choice packet that I've got for you is number 19. Now, I think they may have written it as a pair of parametric equations, but I think it's healthy for us to be able to recognize these things as vector equations as well. And they're going to ask us for the length of the graph of f over the time interval 0 to pi over 2. Okay, so we know the formula for arc length. The formula for arc length is going to be the integral from 0 to pi over 2 of the square root of dx dt squared plus dy dt squared with respect to t. And so I need to take dx dt and dy dt. So start by taking the derivative of cosine cubed, and that will be 3 times cosine squared t times the derivative of cosine is negative sine t. Okay. That's, whoops. And y prime is going to be given by, okay, the derivative of sine cubed t is 3 sine squared t times the derivative of sine t, which is cosine t. And then when we go to square these, sometimes I find it useful to just square them before even trying to put it in the integrand or inside the square root. And so this is 9 cosine fourth t sine squared t. And y prime squared is going to be 9 times the fourth power of sine t times second power of cosine t. So you kind of go through your answer choices and look for an integral that has these in it. So we're looking for 0 to pi over 2 of the square root of 9 cosine fourth t sine squared t and 9 sine fourth t cosine squared t. And that's looking like answer choice D. The next example I've got for you is getting a little towards the particle motion stuff, but we've got an ant crawling along a path modeled by 2 cosine t and 7 sine t. So it's going to be an elliptical path, I'll just tell you. And what direction is the ant moving when it's at point 12 and negative 29? Okay, so we've got x is 12, y is negative 29. I don't think that's the right curve. Hold on just a second. Yeah, I definitely copied the wrong vector equation because 2 cosine t can never equal 12. There's something wrong here. Yeah, definitely wanted that to be x is 3t squared and y is 3t to the third minus 5. Yeah, ants don't walk around ellipses. We know that. And so what direction is the ant moving when it's at point 12, negative 29? Well, I have an x-coordinate and a y-coordinate. But I need the time at which this is happening to figure out kind of the trajectory of the ant. So what I'm going to do is I'm going to solve for t. So probably I just recommend taking the easier looking of the two. Now, you know, if you're really feeling pretty advanced, you could look at y of t and see that it's a one-to-one correspondence. So you could find the unique value of t, whereas x is not injective. So, you know, you could pull back two different answers. Or you could look and say 3t squared equals 12 is something that looks pretty easy for me to solve. And that's exactly what I'm going to do. So I'm just going to say 3t squared equals 12, meaning t squared equals 4, meaning t could be 2 or maybe negative 2. Now, it's only going to be one of these times, probably. So I should just go ahead and check on both of these t values. Okay, when t is 2, y is going to be 3 times 8 is 24 minus 5 is 19. That's not negative 29. Okay, so that's not looking good. So then I try negative 2, and negative 2 to the third is negative 8. 3 times negative 8 is negative 24, minus 5 more is negative 29. Okay, so t is negative 2 at this point. And then we need kind of a trajectory. And, you know, answers to this could be like up and to the left, directly down, down and to the right, something like that. And we're going to take the derivatives of x and y to figure out, you know, if x and y are increasing or decreasing and answer based on that. Now, I'll just tell you, this is the type of problem that makes a really good multiple choice item, you know, like A up and to the left, B up and to the right, C down and to the left, D down and to the right, E directly to the left, or something like that, you know. So the trajectory, I'm going to need the derivative of x, that's going to be 6t. And y prime is going to be 9t squared. And then you plug in t equals negative 2. So that's x prime is negative 12. And y prime is going to be 9 times 4 is 36. Okay. Now, if x prime is negative, that means that x is decreasing, meaning the thing is going to the left. And then if y prime is positive, that means that y is increasing, meaning the thing is going up. So it would be up and to the left. Next, I'm going to ask, in which quadrant is the ant's path concave down? Okay, well, we can do that. We just need to, we know that concave down means the second derivative is negative. So we need to find the second derivative of y with respect to x both times, and then analyze its sign somehow. So we're going to need to take the second derivative. So let's start by just taking the first derivative. Okay, dy dx, we know dy dx is the derivative of y divided by the derivative of x. So it's going to be 6t squared, or 9t squared, over 6t, which again is something I'm going to want to simplify. Now I promise it's not always going to work out to be 3/2 t. All right, and then I know that to get the second derivative, I take the derivative of dy dx, and I divide by dx dt. Okay, so I take the derivative of 3/2 t, and that's just going to be 3/2. And then I'm going to divide by dx dt, which was 6t. And then, I have this. Okay, so this is, I could also say that, 3 divided by 12 is like 1 over 4t. That's how you felt. You could also leave it as 3 over 12t. No difference. I can see that well, I need I'm just going to write over here, I need, in order for the thing to be concave down, I'm going to need the second derivative to be negative. And the only way I can see that this fraction is going to be negative, this 1 over 4t, is going to be if t is negative. Okay, so I'm going to say that this happens if and only if t is negative. And then we go back into x and y and see what happens when we plug in a negative number. So when t is negative, and I plug a negative number into 3t squared, 3t squared is going to actually be positive, right? Because you take a negative number and you square it, it becomes positive, and you multiply it by 3, and it's even larger and still positive. And then you look at 3t to the third minus 5. Well, you take a negative number and you plug that in to 3t to the third minus 5, and it's going to become more negative when you cube it. And then you multiply by 3, still negative, subtract 5 more. Okay, this is going to be a negative number. So this means that x is positive and y is negative. Okay, so, if you're having trouble, okay, we're seeing x is going to be positive over here, and y is negative down here. And so this is quadrant 4. Okay, so the curve will be concave down in quadrant 4. Okay, so next I've got a curve gamma defined by 2 cosine t and 7 sine t. What we're going to ask is curve gamma concave up or concave down at t equals pi over 6. Now, if you happen to remember that this is tracing the path of an ellipse, and t equals pi over 6, okay, I'm expecting this thing, okay, 2 cosine means it's only going out 2 in the x direction, and 7 sine, that's a pretty rough looking ellipse. But at t equals pi over 6, this thing looks like it's frowning, right? So I'm going to expect this thing to come back concave down. Okay, so I need the second derivative, so I need dy dx. Okay, dy dx is the derivative of y, which is 7 cosine t, divided by negative 2 sine t. And now again, you can keep it the way it is and then use the quotient rule when you go to take the second derivative. Or you could not. You could simplify cosine over sine into cotangent and use the derivative of that. And it's been just long enough since we've taken the derivative of cotangent that I think it's a good time to remind you all about that. Okay, so this is negative 7/2 cotangent t. Okay, now we know that we get the second derivative by taking the derivative of dy dx and then dividing by dx dt. So this is going to be the derivative of negative 7/2 cotangent t. So it's negative 7/2, and it's like, oh, what is the derivative of cotangent t? Does anybody remember what the derivative of cotangent t is? Yes? Yes, negative cosecant squared. See, even I have to think about this a little bit. So this is negative cosecant squared. So it's going to become positive 7/2 cosecant squared t. And then I'm going to divide by dx dt, which was negative 2 sine t. All right. And now cosecant squared, I'm not very good at, evaluating that. So what I'm going to do instead is I'm just going to rewrite this as okay, so this will be 7/4, negative 7/4, I guess, times 1 over sine squared pi over 6 times, well, really sine cubed, right? So it's going to multiply in another sine. Okay, now I know that sine of pi over 6 is positive because pi over 6 is in the first quadrant, so the y-coordinate would be positive. And so I've got a negative number times a positive number is negative, meaning that the curve is concave down, as I expected.